On July 1st, 2025, we caught something crossing our solar system. At first glance, just another comet. Icy, distant, unremarkable. But then astronomers did the math on its trajectory, and the room went quiet. Because 3I-ATLAS isn't wandering, it's arriving. With surgical precision, it's braking at Jupiter's gravitational boundary, the exact altitude you'd choose if you wanted to deploy something to the moons below. We weren't bypassed by accident. Earth's oceans are already spoken for, too crowded, too messy. But Europa and Ganymede, still empty, still waiting. And if the calculations are correct, we're watching the seeding happen in real time. Stay with me until the end, because what's unfolding at Jupiter might rewrite everything we thought we knew about being alone. If you're as captivated by this cosmic puzzle as I am, go ahead and like this video and subscribe so you catch every development as this story continues to unfold. Leave a comment telling me where you're watching from, what time it is there, and what you think about this new development. Part 1. The March 16th Problem. Why 3I-ATLAS is only slowing down for Jupiter. On July 1st, 2025, astronomers at the Atlas Survey Telescope in Chile spotted something moving against the stars. At first, it looked like any other comet, a chunk of ice and rock tumbling through space. They catalogued it, gave it a designation, 3I-ATLAS. The third interstellar object ever discovered, another visitor from beyond our solar system, passing through on its way to nowhere in particular. Except, it wasn't passing through. Not really. And the place it was going, the place it had always been going, was Jupiter. More specifically, the exact edge of Jupiter's gravitational territory, the boundary where Jupiter's influence ends and the Sun's begins. A place called the Hill Sphere, located precisely 53.5 million kilometers from the giant planet's center. Now, here's where things get uncomfortable. When you plot 3I-ATLAS's trajectory, when you calculate the energy of its orbit and the velocity it's carrying, something emerges that shouldn't be there. This object isn't just flying past Jupiter, it's arriving at the Hill Sphere with almost exactly the right speed to stop, to insert itself into a stable orbit at the edge of Jupiter's domain. Not too fast, not too slow, just right. That's not how comets work. Comets from interstellar space are supposed to be wild things, hyperbolic orbits that scream through the inner solar system and vanish back into the black. They don't break. They don't adjust. They certainly don't arrive at a specific altitude around a specific planet with the precision of a spacecraft docking at a space station. But 3I-ATLAS appears to be doing exactly that. Its perihelion, the closest approach to the Sun, occurred in late October 2025 at about 1.4 astronomical units. That's roughly the distance of Mars from the Sun, a nice safe distance, not too close to get fried, not too far to waste energy. And after that swing, the trajectory bends outward toward Jupiter with a mathematical elegance that makes some researchers deeply uneasy. Because if you were designing a mission to Jupiter, if you wanted to deliver something to the Jovian moons with minimal energy expenditure, this is exactly how you'd do it. You'd come in from interstellar space, use the Sun for a gravity assist, then coast outward to Jupiter and brake at the Hill Sphere. From there, anything you release drifts inward toward the moons, pulled gently by Jupiter's gravity. No fuel required. It's the most energy-efficient insertion method possible. And that's the problem. Natural objects don't optimize for energy efficiency. They don't care about fuel budgets or mission parameters. They just fall. But this object, if the calculations are correct, appears to have been aimed. Think about what that means. To hit the Hill Sphere boundary at the right velocity, you need to know exactly where Jupiter will be months in advance. You need to account for the Sun's gravity, Jupiter's gravity, the speed you're carrying from interstellar space. You need to correct your course. And here's the terrifying part. The best time to do that correction, the moment when no telescope on Earth could possibly see you make the burn, is when you're behind the Sun. During the weeks surrounding perihelion, 3I-ATLAS was on the far side of our star, hidden from view. If it executed a braking maneuver, then we'd never know. The sunlight would wash out any plume, any change in brightness. By the time it emerged, it would just look like a comet following a natural orbit, except that orbit would have been artificially adjusted to match the insertion parameters we're now observing. This is speculation, of course. We have no direct evidence of a burn. but the trajectory speaks for itself, and what it's saying is deeply unsettling. Most comets that visit the inner solar system get flung outward by gravitational interactions, accelerated to higher speeds, sent tumbling back into the interstellar void. That's the natural order of things. You come in, you get whipped around, you leave faster than you arrived. But 3I-ATLAS is doing the opposite. It's shedding velocity, it's positioning itself, and if it reaches that insertion point, if it achieves a stable position at the Hill sphere boundary, then what happens next is no longer a matter of astronomy. It becomes a matter of biology, or technology, or both. Because once you're parked at the edge of Jupiter's gravity well, you can release things, small things, packages, payloads, and they'll drift inward, falling slowly toward the moons, toward Europa and Ganymede and Callisto, toward the buried oceans that might be the most pristine, untouched bodies of water in the entire solar system. And if those payloads contain something, anything, biological or mechanical, then those oceans won't be pristine anymore. We're not talking about contamination in the usual sense, we're talking about seeding. Deliberate introduction of foreign material into an environment that has been isolated for billions of years. It's panspermia, but with intent. Directed panspermia. The hypothesis that life doesn't just spread by accident, drifting on meteorites and cosmic dust, but by design. That somewhere out there, someone is planting seeds, and we might be watching it happen right now, in real time, aimed at our own solar system. The mainstream scientific community treats 3I-ATLAS as a comet. An unusual one, sure, with a strange composition and an interesting orbit, but still just a comet. Ice, dust, rock, nothing more. But the numbers don't lie. The trajectory doesn't lie. If this object is natural, then nature has developed a sense of precision that borders on the supernatural. And if it's not natural, if it's something else, then the implications are so enormous that most people would rather not think about them at all. Because if 3I-ATLAS is a seeder ship, if it's here to plant something in the Jovian system, then Earth wasn't the target. We were bypassed, ignored, deemed unsuitable for whatever experiment or colonization effort this represents. And that raises a question nobody wants to ask. Why? Part 2. The Payload Hypothesis. Titans. Spore vectors versus cryogenic nanofactories. We don't know what's inside 3I-ATLAS. That's the first thing to understand. All we can see is the outside, a nucleus of ice and rock, maybe a few kilometers across, surrounded by a glowing cloud of gas and dust called the coma. This is standard comet anatomy. When ice heats up near the sun, it sublimates, turning directly from solid to gas, dragging dust particles along with it. The gas scatters sunlight, the dust reflects it, and you get a fuzzy halo that makes the comet visible from Earth. So far, so normal. Except when you look closer, when you analyse the light coming from that coma with spectroscopy, you find something strange. In 2025, the James Webb Space Telescope turned its infrared eyes toward 3I-ATLAS and measured the chemical composition of the gases pouring off its surface. The results were published on the IR-sensitive preprint server, and they raised eyebrows. The coma is dominated by carbon dioxide. Not water vapour, which is what you'd expect from a typical comet, but CO2. The ratio of carbon dioxide to water in 3I-ATLAS is among the highest ever recorded in any comet, solar or interstellar. That's unusual. It suggests this object formed in a very cold, very distant environment, far from any star, where carbon dioxide ice is more stable than water ice. It suggests this thing comes from somewhere truly alien, a place where the chemistry is different, where the rules are different. Now, why does that matter? Because if you wanted to build a container for transporting biological material across interstellar space, you'd want it to be chemically robust. You'd want a composition that can handle temperature extremes, radiation exposure, the long silence of the void. Carbon dioxide ice is stable, it's inert. It can lock organic molecules in place for millions of years without degrading them. Add in water ice, carbon monoxide, dust, and you've got a natural cryogenic freezer, a time capsule that can coast through space indefinitely, preserving whatever's inside until the moment of arrival. This is speculative, obviously. We have no direct evidence that 3I-ATLAS is carrying anything unusual. But the chemistry is suggestive, and when you combine that chemistry with the trajectory, with the precision targeting of Jupiter's Hill sphere, a picture starts to form. A picture of something intentional. something designed. So let's entertain the hypothesis. Let's say 3I-ATLAS is carrying a payload. What could it be? There are two main possibilities, and they're not mutually exclusive. The first is biological. Spores, microbes, dormant cells of some kind, frozen in the ice waiting to be released. This is the directed panspermia scenario, the idea that an advanced civilization is seeding the galaxy with life, spreading it from star to star, from world to world. Why would they do this? Maybe because they can. Maybe because they believe life is precious and should be given every chance to take root. Or maybe for more pragmatic reasons, to terraform, to prepare environments for future colonization, to create ecosystems that can be harvested later. We don't know the motive, but the method would be simple. Pack a comet with hardy microorganisms, aim it at a target system, and let gravity do the rest. When the comet arrives, it releases the spores into the environment, and if conditions are right, they start to grow. Europa and Ganymede are ideal targets for this kind of seeding. Both moons are believed to have subsurface oceans, liquid water trapped beneath kilometres of ice. Those oceans are likely warmed by tidal heating, the constant flexing of the moon's interior caused by Jupiter's immense gravity. That heat could drive hydrothermal vents on the ocean floor, creating energy sources that life could exploit. It's not so different from Earth's deep ocean vents, where entire ecosystems thrive without sunlight, feeding on chemicals rather than photosynthesis. If you dropped microbes into those oceans, and if those microbes were adapted to cold, dark, high-pressure environments, they might survive. They might even thrive. Over time, they could spread, multiply, evolve, creating a biosphere beneath the ice where none existed before. And the beauty of it, from the seeder's perspective, is that it's invisible. The ice shields everything from detection. By the time anyone drills through and discovers what's there, the seeding is complete. The invasion is over. The oceans belong to someone else. That's scenario 1. Scenario 2 is technological. Instead of spores, imagine nanomachines. Microscopic robots or molecular assemblers, frozen in the ice like seeds in soil, waiting for the right conditions to activate. This is the von Neumann probe scenario, named after the mathematician John von Neumann, who theorized about self-replicating machines. The idea is simple but profound. You don't need to send a large spacecraft to explore or colonize a distant system. You just need to send one small, smart machine that can make copies of itself using local resources. Once it arrives, it wakes up, starts gathering materials, and begins the replication process. 1 becomes 2, 2 becomes 4, 4 becomes 8, and so on. Exponential growth. Within a few generations, you could have millions of machines spreading across moons, asteroids, planets, harvesting raw materials, building infrastructure, preparing the system for whatever comes next. Now imagine those machines are packed inside 3I-ATLAS, frozen and inert, travelling through interstellar space for tens of thousands of years. When they reach Jupiter, they're released into the Jovian system, and the ice acts as both transport and raw material. The machines could burrow into the ice shells of Europa or Ganymede, using the water as fuel and building material protected from radiation, hidden from view. They could lie dormant for centuries, waiting for some trigger, some environmental cue, before activating. Maybe they wait for heat. Maybe they wait for human explorers. Maybe they wait for a signal from somewhere else. We don't know, but if they exist, if they're already there or on their way, then the Jovian moons are no longer pristine. They're colonized, occupied, and we're just now starting to suspect it. Both scenarios, biological and technological, share a common logic. They both exploit the unique properties of ice worlds, the protection, the stability, the resources, the isolation. They both rely on patience, on the ability to wait for eons until the moment is right, and they both operate below our current detection threshold. We wouldn't see them with telescopes. We wouldn't detect them with probes. Not until we land, not until we drill, not until we crack open the ice and peer inside. And by then, it might be too late to stop whatever has been set in motion. The mass and energy constraints are important to consider. A payload has to be small enough that it doesn't drastically change the comet's behaviour or trajectory. 3I-ATLAS is estimated to be several kilometres across, but most of that is ice. The actual payload could be much smaller, maybe just a few tons, maybe less. Even a kilogram of engineered microbes or nanomachines could be enough given the right design. Biology is efficient. Technology can be even more so. You don't need a massive ark, you just need the right seeds. And once those seeds are planted, once they start to grow or replicate or spread, the consequences could be enormous. The Jovian moons could become something entirely different from what they are now. They could host alien ecosystems, alien machinery, alien infrastructure, long before any human ever sets foot there. And we would arrive not as discoverers but as latecomers, walking into a world that already belongs to someone else. That's the nightmare scenario. That's what keeps some researchers awake at night, staring at the data, wondering if they're seeing something real or just shadows. Because if 3I-ATLAS is a seeder ship, if it's carrying even one functional payload, then the timeline has already started. The clock is ticking, and we're not ready. Part 3. Europa and Ganymede as virgin basins. Why those oceans matter more than Earth's. Let's talk about water. Not the water in your glass or the water in the ocean outside your window, but the other water, the hidden water. The water locked beneath ice on distant moons, billions of kilometres from the sun, trapped in darkness, untouched by anything resembling life as we know it. Europa, Ganymede, Callisto. These names are familiar to anyone who follows space exploration. They're Jupiter's largest moons, part of the Galilean system, discovered over 400 years ago by an Italian astronomer pointing a crude telescope at the night sky. For centuries they were just dots of light, curiosities, nothing more. Then we sent probes, we took pictures, we measured magnetic fields and surface compositions, and we realised something extraordinary. These moons are not dead rocks. They're oceans. Oceans covered by ice, sometimes tens of kilometres thick, but oceans nonetheless. Liquid water, possibly more water than exists on Earth, sitting quietly beneath frozen shells, isolated from the universe above. And that isolation is what makes them special. That isolation is what makes them targets. Earth's oceans are ancient, but they're not pristine. They're filled with life. Billions of years of evolution, competition, adaptation, complexity stacked on complexity. Every drop of seawater contains millions of microorganisms, viruses, bacteria, archaea, plankton, all fighting for resources, all trying to survive. It's a biological war zone, and it has been for eons. If you wanted to introduce something new into Earth's oceans, something alien, you'd face immediate resistance. The existing biosphere would attack it, compete with it, maybe devour it. There's no guarantee your introduced species would survive, let alone thrive. Earth is messy. Earth is crowded. Earth is unpredictable. But Europa and Ganymede? They're different. If the models are correct, if those subsurface oceans exist, then they're likely sterile, or at least simple. There's no sunlight down there, no photosynthesis, no complex food webs. Any life that might have evolved independently would be sparse, primitive, struggling to extract energy from chemical reactions at hydrothermal vents or from the slow decay of radioactive elements in the moon's core. It's an environment where something new, something introduced, might have a real chance. No competition, no predators, just empty water, waiting to be filled. From the perspective of a civilization interested in spreading life, this is ideal. You don't waste resources seeding a world that's already saturated with biology. You look for blank slates. You look for environments that are habitable but empty. Europa and Ganymede fit that description perfectly. They have liquid water. They have energy sources from tidal heating. They have stable conditions that could support microbial life for billions of years. They're not too hot, not too cold. They're just right, and they're protected. The ice shell acts as a shield, blocking harmful radiation from Jupiter's intense magnetic field, blocking ultraviolet light from the sun, blocking cosmic rays. Anything you plant beneath that ice is safe. It can grow slowly, quietly, without interference from the chaotic universe. Above, it's a greenhouse, a terrarium, a controlled experiment on a planetary scale. And if you're patient, if you're thinking in terms of geological time rather than human time, it's the perfect place to start a new biosphere, or a new factory, or both. Ganymede has an additional advantage. It's the only moon in the solar system with its own magnetic field. That field is generated by a liquid iron core, and it creates a protective bubble around the moon, deflecting some of Jupiter's radiation. This could make Ganymede even more stable, even more hospitable to long-term biological or technological activity. Europa, on the other hand, has a thinner ice shell, which means its subsurface ocean is closer to the surface, easier to access, warmer, more active. Both moons offer different opportunities, different niches. A smart seeder might target both, hedging its bets, maximising the chances of success. And here's the thing. We know these oceans are there. We've seen the evidence. Europa's surface is covered in cracks and ridges, signs of tectonic activity driven by the flexing of the ice shell. Ganymede shows similar features, plus strange magnetic anomalies that suggest a deep, salty ocean. Recent observations from the Hubble Space Telescope and the Juno probe have detected water vapour plumes erupting from Europa's surface, geysers blasting ocean material into space. That material could be sampled, analysed, searched for signs of life. But here's the question. If we find life there, if we detect organic molecules or cellular structures, or anything that looks biological, how do we know it's natural? How do we know it evolved there rather than being planted? That's the contamination problem, and it cuts both ways. We're worried about contaminating Europa with Earth microbes when we send landers and drills. We have strict planetary protection protocols to prevent that. But what if Europa is already contaminated? What if something got there first, decades or centuries ago, carried by an interstellar object we never detected or never understood? Then everything we find is suspect. Every result is ambiguous. We'd be studying alien life, but not the alien life we were looking for. We'd be studying an invasive species, an introduced organism, something that doesn't belong there any more than Earth bacteria would. And we'd have no way to tell the difference, not without a baseline, not without knowing what Europa was like before the seeding began. That ambiguity is dangerous. It undermines the entire scientific enterprise. Astrobiology is built on the assumption that if we find life elsewhere, it evolved independently, that it represents a second genesis, proof that life is common in the universe. But if life is being spread artificially, if civilizations are seeding worlds as a matter of routine, then every discovery is tainted. We'd never know if we're seeing natural life or engineered life, native ecosystems or transplanted ones. The universe becomes a garden, and we're just visitors, wandering through rows of cultivated plots, mistaking deliberate agriculture for wild growth. So why Europa and Ganymede instead of Earth? The answer is obvious once you think about it. Earth is already taken. Earth has a biosphere that's been refining itself for nearly 4 billion years. It's resilient, adaptive, hostile to newcomers. If you dropped alien microbes into Earth's oceans, they'd probably die. And even if they survived, they'd be just one more species among millions, competing for resources, struggling to find a niche. There's no guarantee they'd spread. There's no guarantee they'd matter. But on a sterile moon, the first arrival wins. The first organism to establish itself becomes the foundation of everything that follows. It sets the rules. It shapes the environment. It becomes the ancestor of an entire biosphere. That's power. That's control. And if you're a civilization with the patience and technology to seed distant worlds, that's exactly what you want. You want clean environments. You want predictable outcomes. You want worlds where your biology or your technology can flourish without interference. And you want them far from the noise and chaos of planets like Earth, where anything could happen, where your carefully designed experiment could be ruined by unpredictable variables. So you skip Earth. You aim for the moons. You plant your seeds in the quiet places, the hidden places, and you wait. Because time is on your side, and if you're right, if your seeds take root, then one day those moons will be yours. Not legally, not politically, but biologically, ecologically. They'll be yours because your life is there, your machines are there, your influence is spread into every drop of water, every crack in the ice. And when humans finally arrive, when we drill through the ice and lower our cameras into the dark ocean below, we won't be discovering a new world. We'll be intruding on someone else's. Part 4. The Sentinel Constellation Theory. There's a concept in orbital mechanics called a parking orbit. It's exactly what it sounds like, a stable orbit where you leave something, where it can sit for a long time without falling or drifting away. Satellites use parking orbits, space stations use parking orbits, and if you were designing a mission to monitor or control a distant region of the solar system, you'd use parking orbits too. The Hill sphere around Jupiter is one of the best parking spots in the entire solar system. It's the boundary where Jupiter's gravity is exactly balanced by the Sun's gravity. A shell of space roughly 53.5 million kilometers from Jupiter's center, where objects can remain stable for thousands of years without significant perturbation. If you place something there, it stays there. No fuel required, no course corrections, just patience. And if 3I-ATLAS is positioning itself at the edge of that hill sphere, if it's achieving a stable insertion as the trajectory suggests, then it's not just delivering payloads, it's setting up infrastructure, it's creating a constellation, a network of watchers, monitors, sentinels, parked at strategic points around Jupiter, observing, waiting, ready to act when the time comes. Imagine it this way. 3I-ATLAS approaches Jupiter and breaks at the hill sphere boundary. It achieves a stable orbit. Then it releases a series of small objects, canisters or pods or microsatellites, each one drifting to a slightly different position along the sphere. These objects spread out, forming a ring or grid around Jupiter, covering different angles, different lines of sight. They're not passive debris, they're designed. They have sensors, maybe communication equipment, maybe propulsion systems for fine-tuning their positions. They're relay nodes, data collectors, border posts. They watch the Jovian system, monitoring the moons, tracking activity, detecting any changes. And they wait. They could wait for centuries or millennia without degrading, built to last, designed for the long game. This is the Sentinel constellation theory, and it's chilling because it implies intention. It implies planning on a scale that dwarfs human civilization. We think in terms of years, maybe decades, if we're optimistic. But a civilization capable of sending probes across interstellar space, capable of targeting specific moons around specific planets, is thinking in terms of geological time. They're thinking in terms of ice ages, continental drift, stellar evolution. They're patient, and they're thorough. What would these sentinels do? The possibilities are numerous. They could serve as monitoring stations, passively observing the Jovian system, collecting data on radiation levels, magnetic fields, orbital dynamics, surface activity on the moons. That data could be stored internally or transmitted back to the origin civilization, though transmission across interstellar distances is problematic due to signal degradation and travel time. More likely, the Sentinels store the data and wait for retrieval, or they act autonomously based on pre-programmed instructions. They could serve as navigation beacons marking the territory, signalling to future arrivals that this system is claimed, occupied, under observation. Or they could serve as relay points, coordinating the deployment of payloads from the main comet to the moons below. When 3I-ATLAS releases a cluster of spores or nanomachines, the Sentinels could guide them, using tiny thrusters or magnetic fields, ensuring they reach the correct targets. Europa gets one payload, Ganymede gets another, Callisto gets a third. Precision delivery across millions of kilometers, orchestrated by a network of silent machines. And the most unsettling possibility, the Sentinels could serve as activation triggers. They could be programmed to wait for specific conditions, detecting environmental changes, incoming, spacecraft, increased radiation, anything that indicates the system is being explored or colonized. When those conditions are met, the Sentinels wake up. They activate dormant payloads on the moons. They deploy additional resources. They respond. There's no natural process that creates a constellation of objects parked at hill sphere zones. Natural debris, meteoroids, dust. All of it drifts, falls, gets perturbed by gravitational interactions. It doesn't organize itself into a grid. It doesn't hold station. But artificial objects can. Artificial objects with minimal propulsion, solar panels for power, onboard computers for decision-making. They can maintain precise positions for centuries. And if that's what's happening, if 3I-ATLAS is deploying such a network, then the Jovian system is no longer unclaimed territory. It's occupied, quietly, invisibly, but occupied nonetheless. We wouldn't see the Sentinels with current telescopes. They'd be too small, too dark, too far away. They'd look like noise, like background clutter, easily dismissed. Even if we pointed a probe at one, we might not recognize it as artificial. It could be disguised as a rock, as a chunk of ice, as a fragment of comet debris. By the time we figure out what we're looking at, the mission is already complete, the infrastructure is in place, and we're just starting to catch up. The Sentinel constellation theory appeals to a long-term strategic mindset, the kind of thinking that doesn't care about immediate results, but focuses on establishing a permanent presence. You don't send one probe and hope for the best. You send a network, you build redundancy, you create a system that can survive failures, adapt to changing conditions, and operate autonomously for millennia. It's the difference between a scouting mission and an occupation. Consider the implications for humanity. If the Sentinels exist, if they're already there or arriving soon, then every future mission we send to Jupiter is being watched. Every probe, every lander, every drill we use to pierce the ice of Europa or Ganymede is being monitored. The data we collect is being observed by something else. And if we do something unexpected, something that threatens the seeding operation or the payloads already deployed, the Sentinels might respond. How? We don't know. Maybe they self-destruct to avoid detection. Maybe they activate countermeasures, releasing additional payloads, accelerating the seeding process before we can interfere. Maybe they do nothing, content to observe, trusting that their mission is already complete and human activity won't matter in the long run. Or maybe they signal back across the light years, informing their creators that the system is no longer quiet, that a new intelligence has arrived and is beginning to explore, and then, decades or centuries later, something else arrives, something bigger, something that doesn't need to hide. That's the nightmare. Not the seeding itself, but what comes after. The Sentinels are just the first wave, the reconnaissance. They're setting the stage, preparing the ground, marking the territory. When the real colonizers arrive, when the civilization that sent 3I-ATLAS decides it's time to claim what they've seeded, humanity might be in the way. We might be irrelevant, or we might be a problem to be solved. Either way, we won't have a say. The Hill sphere isn't just a boundary. It's a strategic position, a high ground in the geography of space. Whoever controls it controls access to the moons below. And if 3I-ATLAS is establishing that control, if it's deploying Sentinels and payloads with precision and patience, then the Jovian system is already lost. We just don't know it yet. We're still operating under the assumption that space is empty, that the moons are pristine, that we're the first to arrive. But what if we're not? What if we're generations late, arriving at a world already shaped by someone else's design? Then exploration becomes archaeology. We won't be discovering life. We'll be uncovering someone else's project, someone else's experiment, someone else's claim, and we'll have to decide, do we interfere, do we try to stop it, or do we step back, acknowledge that we're outmatched and accept that the universe is already being managed by forces far beyond our control? The Sentinel constellation theory forces us to confront that possibility. It forces us to consider that 3I-ATLAS isn't an anomaly, but a harbinger. And if it's true, if the Sentinels are real, then the universe is far more crowded, far more organised, and far more dangerous than we ever imagined. Part 5. The Indifference to Earth. A Statistical Red Flag. 3I-ATLAS never came close to Earth. That's a fact. Publicly available orbital data shows that throughout its entire journey through the inner solar system, the comet maintained a safe distance from our planet. No near miss, no collision risk, not even a close flyby. From a planetary defence perspective, this is good news. We weren't in danger. But from a strategic perspective, if you're entertaining the hypothesis that this object is artificial, if you're considering the possibility that it's a targeted mission, rather than a random interloper, the avoidance of Earth becomes significant. It becomes a choice, and choices imply intent. Why would an interstellar object, if it were carrying payloads designed to seed life or deploy technology, skip Earth entirely and focus on Jupiter's moons? The answer depends on what you're trying to accomplish. If your goal is to introduce life into a system, to create a new biosphere or a new technological infrastructure, then you need the right environment. You need stability, resources, predictability. Earth offers none of those things, at least not from the perspective of an outside observer. Earth is chaotic. Earth is already filled with life, billions of years of evolutionary competition, a biosphere that's aggressive, adaptive, and deeply entrenched. If you tried to introduce something new, something foreign, into Earth's oceans or atmosphere, it would face immediate resistance. The existing organisms would attack it, consume it, outcompete it. There's no guarantee your introduced species would survive, let alone spread. And even if it did survive, it would just become one more thread in an already tangled web, indistinguishable from the native life, impossible to track or control. Earth is messy, it's unpredictable, it's a terrible choice for a controlled seeding operation. But the icy moons of Jupiter, they're different. They're quiet. They're simple. They're isolated beneath kilometres of ice, shielded from the chaos of the solar system, locked in stable orbits that have barely changed in billions of years. If the subsurface oceans are sterile or nearly sterile, then anything you introduce becomes the dominant life form. It doesn't have to compete. It just has to survive. And survival, in a stable environment with liquid water and energy from tidal heating, is much easier than competition in Earth's crowded biosphere. From a seeder's perspective, the choice is obvious. You skip the noisy planet and focus on the blank slates. You prioritize environments where your biology or technology can flourish without interference. And that's what makes the trajectory of 3I-ATLAS so suspicious. If it were a random object, you'd expect it to follow a random path, maybe passing near Earth by chance, maybe not. But this object's trajectory avoids Earth and targets Jupiter with apparent precision. That's not random, that's strategic. Now, let's talk statistics. The odds of an interstellar object entering the solar system, swinging past the Sun, and then arriving at Jupiter's Hill sphere with exactly the right velocity to insert into a stable orbit are extraordinarily low. Interstellar space is vast, and the range of possible trajectories is enormous. Most objects would either pass through too quickly, escaping back into the void, or fall too steeply into the Sun, getting destroyed or flung outward by gravitational interactions. The parameter space for achieving a precise Hill sphere insertion is tiny, a needle in a haystack. And yet, if the analysis is correct, that's exactly what 3I-ATLAS is doing. It's threading the needle. Now, you could argue that we're just lucky, that we happen to catch the one interstellar object in a million that just happens to have this unusual trajectory. Or you could argue that the trajectory isn't unusual at all, that it's designed, that someone or something calculated the required velocity, the required angle, the required timing, and launched this object accordingly. The latter explanation requires accepting the existence of an advanced extraterrestrial intelligence with the capability to send probes across interstellar space. That's a big assumption. But the former explanation requires accepting a statistical coincidence so unlikely that it borders on the miraculous. Neither option is comfortable. The mainstream scientific community predictably leans toward the natural explanation. 3I-ATLAS is treated as an interstellar comet similar to 2I Borisov, which visited the solar system in 2019. Observations show typical cometary activity: outgassing, a coma, a dust tail. Spectroscopy reveals a composition consistent with ices and volatiles, nothing obviously artificial. There's no radio signal, no unusual heat signature, no signs of propulsion or course correction that we can detect. To most astronomers, it looks like a comet, behaves like a comet, and therefore is a comet. End of story. But a small vocal minority, mostly outside the mainstream, isn't convinced. They point to the trajectory, the targeting precision, the unusual composition, and they ask questions. Why is the CO2 to water ratio so high? Why does the orbit match the insertion parameters so closely? Why does it seem to avoid Earth while heading toward Jupiter? These questions don't have easy answers within the natural framework, and when questions pile up, when coincidences multiply, skepticism grows. Not enough to overturn the mainstream consensus, not yet, but enough to keep the conversation alive, enough to plant doubt. If Earth was skipped on purpose, if 3I-ATLAS is indeed an artificial object targeting the outer system, then the implications extend far beyond astrobiology. It means we're not alone. It means there's an intelligence out there with the capability and the motivation to seed distant systems. It means the universe is being actively managed, gardened, cultivated, and it means humanity is not the primary focus of that cultivation. We're bystanders. We're irrelevant. The real action is happening at Jupiter, beneath the ice of Europa and Ganymede, in the quiet oceans where something new is taking root. That realization, if it ever becomes widely accepted, would be one of the most profound shifts in human understanding since Copernicus told us we weren't the centre of the solar system. We're not even the centre of the seeding operation. We're just noise, organic clutter on a crowded planet, bypassed in favour of cleaner, simpler targets. And that's terrifying. Not because it means we're in danger, but because it means we don't matter. We're not the story. We're a footnote. The real story is unfolding millions of kilometres away, in places we've barely begun to explore, and by the time we get there it might already be over. The seeds will have sprouted. The machines will have replicated. The oceans will belong to someone else, and we'll arrive late to a party we were never invited to, wondering why no one told us the universe was already occupied, already claimed, already divided up among civilizations far older and far more patient than our own. That's the indifference to Earth. That's the statistical red flag. And if you're paying attention, if you're willing to entertain the uncomfortable possibility that 3I-ATLAS is more than just a comet, then that flag is waving right in front of you, impossible to ignore. Part 6. The Architect's Signature. Pattern Recognition in Interstellar Interlopers. Before 3I-ATLAS there were two confirmed interstellar objects that visited our solar system, passed through, and left us with more questions than answers. The first was Oumuamua, discovered in October 2017 by the Pan-STARRS telescope in Hawaii. It was strange from the start, elongated, tumbling, reddish in colour, with no visible coma or tail despite passing close to the Sun. It moved too fast to be bound to our star, its trajectory clearly hyperbolic, confirming it came from somewhere else. And then, as it departed, it accelerated. Not much, just a tiny push, too small to be a rocket but too large to ignore. Scientists proposed outgassing as the explanation, that volatile ices on the surface were sublimating and acting like a natural thruster. But Oumuamua didn't look icy, it looked dry, and the acceleration didn't match the expected pattern for outgassing, so the mystery remained. Then came 2I Borisov, discovered in August 2019 by Crimean astronomer Gennady Borisov. This one was different. It looked like a comet, acted like a comet, had a visible coma rich in carbon monoxide and other gases. It was reassuringly normal, a reminder that not every interstellar visitor needs to be weird. Borisov passed through, we studied it, and it left. Case closed, or so we thought. Now we have 3I-ATLAS, and it's bringing back the weirdness. It has a coma, yes, so it's not as dry as Oumuamua, but the composition is unusual, dominated by carbon dioxide, with a CO2 to water ratio higher than almost any comet we've ever seen, and the trajectory, as discussed, appears to target Jupiter with suspicious precision. So where does that leave us? 3 interstellar objects, 3 completely different profiles. Oumuamua, dry, elongated, accelerating. Borisov, normal, cometary, unremarkable. 3I-ATLAS, CO2 rich, potentially targeting. No obvious pattern. Except maybe there is a pattern, and we're just not seeing it yet. What if these objects aren't random? What if they belong to different classes, different types of interstellar probes, each designed for different purposes? Oumuamua could be a scout, a fast-moving reconnaissance probe, built to pass through quickly, gather data and move on. Its unusual shape and acceleration might be intentional design features, optimized for speed and maneuverability. Borisov could be a decoy, a natural-looking object meant to blend in, to make us think interstellar visitors are unremarkable, nothing to worry about. And 3I-ATLAS could be a seeder, a payload carrier, built to deliver biological or technological material to specific targets within the system. 3 objects, 3 missions. Or maybe we're overthinking it. Maybe they're all just space rocks, frozen debris from star formation, ejected from distant systems and wandering the galaxy. The universe is big, and the number of rogue objects out there, comets and asteroids kicked out of their home systems by gravitational interactions, is staggering. Statistical models suggest that interstellar visitors should be relatively common, passing through the inner solar system every few years on average. We're just now starting to detect them because our telescopes have gotten better, so maybe there's no pattern, maybe it's all coincidence. But here's the thing about patterns. You only see them when you have enough data points. 3 objects isn't a lot. But if we keep watching, if we detect more interstellar visitors over the next decade or two, and if those visitors start showing repeated features, repeated behaviours, then the pattern becomes harder to dismiss. Imagine we detect a 4th object and it has a high CO2 composition like 3I-ATLAS, then a 5th and it accelerates like Oumuamua, then a 6th and it targets Saturn's moon Enceladus, another ice world with a subsurface ocean. At some point, the coincidences pile up so high that you can't ignore them anymore. You're forced to consider the possibility that these objects are part of a larger fleet, a coordinated effort, an interstellar campaign to seed or survey the galaxy. And if that's true, if there's a pattern, then there's an architect. Someone, or something, is designing these missions, launching these probes, sending them out across the void with specific goals in mind. The question becomes who and why, and what are they trying to accomplish? One hypothesis, and it's a fringe one, is that advanced civilizations use preferred trajectories for their probes, paths through the galaxy that minimize energy expenditure and travel time. These would be the interstellar equivalent of trade routes or highways, following the gravitational contours of the Milky Way, taking advantage of stellar motion, avoiding dense regions where debris and radiation are high. If such routes exist, then probes using them would naturally cluster along certain trajectories, entering solar systems from similar directions at similar velocities. That would create a pattern, and if 3I-ATLAS is following such a route, then we might expect future interstellar visitors to follow similar paths, entering the solar system from roughly the same region of the sky, heading towards similar targets. That's testable. We just need more data. The counter-argument is straightforward. Natural interstellar objects should show wide diversity because they're ejected from a wide variety of systems under a wide variety of conditions. You'd expect different compositions, different shapes, different trajectories, reflecting the diversity of their origins. And so far, that's what we've seen. Oumuamua, Borisov and 3I-ATLAS are all different. So maybe there's no architect. Maybe it's just chaos. But chaos doesn't explain precision. Chaos doesn't explain targeting. If 3I-ATLAS is truly inserting itself into Jupiter's hill sphere with minimal energy, if the trajectory is optimized rather than random, then chaos stops being a satisfying explanation. You need something more. You need intent. And once you admit the possibility of intent, once you open that door, everything changes. Because if one interstellar object is artificial, then how many others are? How many have we missed? How many passed through the solar system before we had telescopes capable of detecting them? The universe could be filled with these things, silent probes drifting from star to star, seeding worlds, gathering data, building infrastructure, all operating on timescales so long that individual civilizations rise and fall without ever noticing them. That's the tip of the iceberg scenario. We're seeing a tiny fraction of what's actually out there, and the rest is invisible, hidden in the noise, camouflaged as natural objects, waiting to be discovered or ignored. And if we're surrounded by an invisible network of alien probes, if the galaxy is already colonized or at least surveyed, then humanity's place in the universe is very different from what we've always assumed. We're not pioneers, we're latecomers. The frontier was claimed long ago, and we're just now waking up to that fact. That's what pattern recognition in interstellar interlopers could reveal. Not proof, not yet, but a growing suspicion that the universe is more crowded, more organized, and more intentional than we ever imagined. Part 7. The Galactic Garden Hypothesis and the Ethics of Cosmic Agriculture. Think of the galaxy as a garden, not the chaotic wilderness we imagine, full of random stars and planets scattered across the void, but an organized space where certain regions are tended, certain worlds are cultivated, and certain civilizations act as gardeners. This is the Galactic Garden Hypothesis, and it's both beautiful and terrifying. The idea is simple. Advanced civilizations, those that have survived long enough to master interstellar travel and biological engineering, don't just explore the galaxy, they shape it. They seed planets and moons with life, carefully selecting environments that are habitable but empty, creating new biospheres from scratch. It's not random. It's agriculture. Cosmic-scale agriculture, where the crops are ecosystems, the fields are planets, and the harvest might not come for millions of years. If this hypothesis is correct, then 3I-ATLAS isn't an anomaly. It's a tool, a delivery mechanism for biological or technological payloads sent to prepare worlds for future use. And the targets, Europa and Ganymede, are ideal because they're exactly what a gardener would look for. Stable, water-rich, isolated, and, most importantly, empty. Let's break down why ice moons are such attractive candidates for seeding. First, water. Life as we know it requires water, or at least most forms of life do. Europa and Ganymede have more liquid water than Earth, locked beneath their ice shells, warmed by tidal heating. That water is chemically rich, possibly containing salts, minerals, maybe even dissolved gases that could support metabolism. It's not just water, it's an environment. Second, energy. Tidal heating provides a constant energy source, driving convection in the oceans, possibly creating hydrothermal vents on the ocean floor. That's the same energy source that supports life at Earth's deep-sea vents, ecosystems that thrive without sunlight, feeding on chemicals rather than photosynthesis. If you wanted to seed a moon with life, you'd want those vents. They're stable, predictable, and rich in chemical energy. Third, stability. Ice moons don't have weather, tectonic shifts, or atmospheric chaos. Their environments change slowly over geological timescales, which makes them perfect for long-term experiments. You can plant something there and come back a million years later, and it'll probably still be recognisable, still following the evolutionary path you set in motion. Fourth, protection. The ice shell shields everything beneath it from radiation, solar flares, cosmic rays, all the hazards that make space so hostile. It's a natural barrier, a greenhouse that keeps the interior safe and stable. And finally, isolation. Ice moons are far from the sun, far from Earth, far from the noise and interference of complex biospheres. They're quiet. They're out of the way. If you're conducting an experiment, if you're seeding life or deploying technology, you want isolation. You don't want variables you can't control. Now contrast that with Earth. Earth is crowded. Every ecological niche is filled. Every resource is contested. The oceans are teeming with life. The atmosphere is saturated with gases produced by biological activity. The land is covered in plants, animals, fungi, bacteria, all competing, all adapting, all trying to survive. If you tried to introduce something new, something alien, it would face immediate competition. Maybe it would win, maybe it would lose, but either way it's a gamble. You can't control the outcome, and from a gardener's perspective that's a problem. You don't plant seeds in a field full of weeds. You clear the field first, or you find a new field, one that's empty and ready. Earth is the weed field. Europa and Ganymede are the empty fields. So you skip Earth, you focus on the moons, and that's what makes the trajectory of 3I-ATLAS so significant. If it's avoiding Earth and targeting the moons, it's making the same choice a rational gardener would make. Now, let's talk about ethics. From a human perspective, seeding an alien moon with life or technology feels like an invasion. It's contamination, interference, a violation of a pristine environment. We have planetary protection protocols precisely to prevent this kind of thing. But from the gardener's perspective, it might feel like creation. They're not destroying life, they're creating it. They're taking a sterile world and giving it a biosphere, transforming ice and water into a living ecosystem. Is that wrong? Is it colonization? Or is it terraforming? Is it theft? Or is it gift? The answer depends on your perspective, and there's no universal morality to settle the question. Consider the possibility that Earth itself was seeded, that life didn't arise here naturally through random chemistry and lucky accidents, but was introduced, planted, nurtured by some ancient civilization that passed through billions of years ago. Panspermia, the idea that life spreads between worlds, is a legitimate scientific hypothesis. Most versions assume it happens naturally via meteorites or comets carrying microbes. But directed panspermia, the idea that it's intentional, that someone is doing it on purpose, is just an extension of the same concept. If Earth was an experiment, if our biosphere was planted by cosmic gardeners, then everything we are, everything we've evolved into is part of their design. Maybe that experiment succeeded beyond their expectations, and Earth became a wild, chaotic success story. Or maybe it diverged from the plan, became too unpredictable, too messy, and they decided to start fresh elsewhere. Maybe that's why 3I-ATLAS skips Earth. We're the abandoned plot, the experiment that got away, and now they're trying again, this time on cleaner worlds, simpler targets, places where they can control the outcome. It's unsettling to think of humanity as a failed experiment, but it's also humbling. It forces us to consider that we're not the centre of the story, not the pinnacle of cosmic achievement. We're just one more attempt in a long series of attempts, one more thread in a vast tapestry being woven across the galaxy. The long-term vision of a civilization engaged in cosmic agriculture is staggering. They're not thinking in terms of decades or centuries. They're thinking in terms of millions of years, planning for contingencies that won't arise until stars have moved, orbits have shifted, ice ages have come and gone. They're patient because they have to be. Seeding a world isn't a quick process. You plant the seeds, you wait for them to take root, you wait for evolution to do its work, and eventually, maybe you return to harvest or observe or integrate the new biosphere into your larger plans. But that return might not happen for eons. The original civilization might be gone, replaced by their descendants or by someone else entirely. The garden might outlive the gardener. And that's fine, because the point isn't immediate profit. The point is legacy. The point is shaping the galaxy over timescales that make individual lifetimes irrelevant. If the galaxy is a garden, then we're living in someone else's plot. We didn't plant these seeds, we didn't tend this soil, but we're growing here anyway, and maybe that was always the plan. Maybe the gardeners knew that life, once started, takes on a life of its own, becomes unpredictable, chaotic, beautiful in its complexity. Maybe that's what they wanted, or maybe we're just weeds, and 3I-ATLAS is here to plant the real crop, the one they actually care about, in the quiet moons where we won't interfere. Part 8. Covert Debates Inside Space Agencies. There are conversations happening right now behind closed doors in conference rooms at NASA, ESA, JAXA and other space agencies around the world. Conversations about risk, about contamination, about what happens if we're wrong. Publicly, these agencies treat 3I-ATLAS as an interstellar comet. The press releases are careful, measured, emphasizing the scientific opportunity, the chance to study a pristine object from another star system. There's no mention of alien probes or seeding missions. That would be irresponsible, premature, alarmist. But privately, some scientists are asking uncomfortable questions. What if? What if 3I-ATLAS isn't just a comet? What if it's carrying something? What if by the time we send missions to Europa or Ganymede in the 2030s or 2040s, those moons are already contaminated? Not by us, but by something else. And if that's true, how do we even know? How do we distinguish between native life, if it exists, and introduced life from an alien source? These questions don't have easy answers, and they create dilemmas that current protocols aren't designed to handle. Planetary protection is a big deal in space exploration. The goal is to avoid contaminating other worlds with Earth microbes, and to avoid bringing back alien organisms that could harm Earth's biosphere. NASA has strict sterilization procedures for spacecraft heading to potentially habitable environments like Mars or Europa. Every surface is cleaned, every component is baked or irradiated, reducing the microbial load to near zero. It's expensive and time-consuming, but it's necessary to preserve the scientific integrity of future missions. If we find life on Europa, we need to be confident it's not something we accidentally brought there on a lander or drill. But the protocols assume contamination comes from us. They don't account for the possibility that contamination might come from someone else, from an interstellar visitor that arrived decades before we even launch our missions. If 3I-ATLAS deploys biological payloads into the Jovian system, if those payloads reach Europa or Ganymede and successfully seed the subsurface oceans, then by the time we drill through the ice, we won't be discovering native life. We'll be discovering alien-introduced life. And unless we have some way to distinguish the two, unless we can identify biomarkers or genetic signatures that indicate non-terrestrial origin but also non-native origin, we'll be fooled. We'll claim we've found proof of abiogenesis, proof that life arises independently in multiple places, when in reality we're just seeing evidence of panspermia. That false positive undermines the entire scientific enterprise. It invalidates our conclusions, and it raises the question, how many other worlds have we misidentified? How many times have we found life and assumed it was native when it was actually introduced? Internally, some mission planners are reportedly pushing for additional safeguards, not just to prevent Earth contamination, but to account for the possibility of prior alien contamination. This might include more detailed chemical and genetic analysis of any samples we collect, looking for patterns that don't match known biochemistry, isotopic ratios that suggest non-solar system origin, or structures that appear engineered rather than evolved. It also might include revisiting the ethics of drilling into subsurface oceans. If there's even a small chance that those oceans have already been seeded, then breaking through the ice could disrupt an ongoing experiment, interfere with an alien project, or trigger unintended consequences. What if the payloads deployed by 3I-ATLAS are dormant, waiting for some environmental cue to activate? What if human drilling provides that cue? Then we're not just contaminating, we're activating. We're turning on something that was designed to stay off until conditions were right, and we have no idea what happens next. These are worst-case scenarios, and most scientists would argue they're too speculative to guide policy. But the problem with worst-case scenarios is that you don't get advance warning. By the time you realise you're in one, it's too late to change course. There's also the issue of public communication. If space agencies seriously entertain the possibility that 3I-ATLAS is an alien probe, if they discussed it openly, the reaction would be intense. Media hysteria, conspiracy theories, political pressure, funding battles, all the chaos that comes with challenging established narratives. It's easier to stick with the safe story. It's just a comet. And maybe it is. Maybe all this speculation is unfounded, and 3I-ATLAS will pass through, release nothing, and fade into the background like Borisov did. But the quiet data revisions some observers claim to have noticed, the adjustments to orbital parameters or brightness curves after anomalies were raised, suggest that not everyone is comfortable with the official narrative. Whether those revisions represent legitimate corrections based on better data or subtle pressure to downplay weirdness is impossible to say without access to internal communications. But the fact that the question is even being asked, the fact that amateur astronomers are scrutinizing every data release looking for signs of suppression, indicates a level of distrust, and that distrust is corrosive. It undermines the credibility of institutions that rely on public support and funding. If people start believing that space agencies are hiding information, even if that belief is unfounded, it damages the entire enterprise. So what should be done? Transparency is the obvious answer, but transparency is complicated. Not all data can be released immediately. Some requires processing, verification, peer review, and some data, if misinterpreted, can cause more harm than good. Imagine releasing raw spectroscopy data showing an unusual chemical signature in 3I-ATLAS's coma, something that could be interpreted as artificial or biological. Without context, without careful analysis, that data would be seized upon by sensationalists turned into headlines, distorted beyond recognition. By the time the scientific community clarifies that the signature is actually consistent with natural processes, the damage is done. The narrative is set. So agencies are cautious. Maybe too cautious. Maybe not cautious enough. It's a balancing act, and nobody has perfect information. What's clear is that 3I-ATLAS, whether it's a comet or something else, has exposed gaps in our frameworks, gaps in how we think about contamination, exploration, and the possibility of encountering alien activity. Those gaps need to be addressed before we send humans or sophisticated probes to the outer moons, because if we're not prepared, if we walk into a situation we don't understand, we might make mistakes we can't undo. And in space, mistakes have consequences that last for geological timescales. Part 9, Conspiracies and Counter-Conspiracies. Who's controlling the narrative? Let's talk about narrative control. Every major discovery, every anomaly, every piece of data that doesn't fit the standard model creates tension between those who see it as evidence of something new and those who see it as noise. With 3I-ATLAS, that tension is palpable. On one side, you have the astronomical community, trained to be skeptical, to demand extraordinary evidence for extraordinary claims, to default to natural explanations until natural explanations fail. On the other side, you have amateur observers, independent researchers, and a growing number of people who suspect that something is being overlooked or deliberately downplayed. The result is a kind of information war, fought not with weapons, but with data, interpretations, and trust. And in that war, the question isn't just what's true, it's who gets to decide what's true. Let's start with the claims of quiet data revisions. Some observers, watching 3I-ATLAS closely, have reported noticing changes in publicly available orbital parameters or photometric data after they raised questions about anomalies. For example, an early brightness measurement might have shown an unexpected spike, suggesting outgassing or structural changes. Later, that data point is revised, smoothed, normalized, and the spike disappears. Is that legitimate correction, based on better calibration or more accurate observations? Or is it suppression, an attempt to make the data look more normal, less suspicious? Without access to the raw data and the processing pipeline, it's impossible to say. But the perception of suppression, justified or not, fuels conspiracy theories. People start asking who benefits from keeping 3I-ATLAS in the just a comet category. Space agencies, who don't want the headache of dealing with alien probe speculation. Governments, who prefer not to alarm the public. Private interests, who might see strategic advantage in controlling information about extraterrestrial activity. Or scientists themselves, who worry that entertaining wild hypotheses will damage their credibility and funding prospects. All of the above are plausible motives, which makes the conspiracy narrative sticky. It sticks because it's not entirely crazy. History is full of examples where institutions suppressed or delayed releasing information for political, economic, or social reasons. Watergate, the Tuskegee experiments, classified military programs, all cases where the official story didn't match reality, and the truth only emerged later, after leaks or investigations. So when people see anomalies in 3I-ATLAS data, and then see those anomalies quietly disappear, they draw parallels, they assume the worst. And once that assumption takes hold, it's hard to dislodge, even with transparent explanations. Now, the counter-narrative is equally important. Many of the claimed anomalies, when examined closely, turn out to be artifacts, image processing errors, where noise in the detector gets mistaken for structure, calibration issues, where brightness measurements vary depending on the telescope, filter, or atmospheric conditions, natural comet behavior, where brightness fluctuates due to outgassing, rotation, or changes in viewing geometry. All of these can mimic something unusual, something artificial, but they're just mundane features of observational astronomy. The problem is that distinguishing signal from noise requires expertise, access to the data, and time. Most people don't have those resources, so they rely on summaries, interpretations, and opinions from others, and in that environment, misinformation spreads fast. Social media amplifies everything. Someone posts an enhanced image of 3I-ATLAS, claiming to see geometric structures or a metallic sheen. That image gets shared, commented on, analysed by amateurs with varying levels of knowledge. Within days, it's embedded in the discourse, treated as evidence, even if the enhancement was just aggressive contrast adjustment that brought out noise. Debunking requires effort, patience, and often goes unnoticed because it's not as exciting as the original claim. So the conspiracy narrative grows, fed by a mix of genuine curiosity, pattern recognition run amok, and distrust of institutions. Meanwhile, the scientific community gets frustrated. They see their careful work misinterpreted, their data cherry-picked, their conclusions ignored in favour of sensationalism. They push back, sometimes dismissively, sometimes condescendingly, which only deepens the divide. Both sides think the other is biased. Both sides think there's defending truth. And in the middle, the actual truth about 3I-ATLAS, whatever it is, gets obscured. Who's controlling the narrative? Nobody and everybody. There's no central authority dictating what people believe about 3I-ATLAS. Instead, there's a chaotic marketplace of ideas, where different narratives compete for attention, credibility, and influence. The mainstream scientific narrative has institutional support, peer review, and the weight of established methods. The alternative narratives have flexibility, creativity, and the appeal of challenging authority. Neither has a monopoly on truth. Both are shaped by biases, incentives, and limitations. What's frustrating is that the question of whether 3I-ATLAS is artificial or natural is in principle answerable. We have the tools. We can measure its composition, track its trajectory, search for signals, analyse its behaviour. But those tools require resources, coordination, and time. And in the meantime, speculation fills the void. People want answers now, and when official sources don't provide them, or provide them in jargon-heavy papers that take months to publish, alternative sources step in. The ethical question here is about transparency and trust. If space agencies suspect, even slightly, that 3I-ATLAS might be artificial, do they have an obligation to say so publicly? Or do they have an obligation to remain silent until they're certain, to avoid causing panic or spreading misinformation? There's no easy answer. Transparency builds trust but can also create chaos. Caution preserves order but breeds suspicion. The balance is delicate, and 3I-ATLAS, with its ambiguous data and provocative trajectory, sits right on that edge. So we're left with a narrative landscape that's fragmented, contested, and evolving. Some people believe 3I-ATLAS is a comet, nothing more. Some believe it's a probe, a seeder, a harbinger of something larger. Some are agnostic, waiting for more data. And some are convinced there's a cover-up, that the truth is being hidden, that someone somewhere knows more than they're telling. All of these positions are understandable. All of them reflect different ways of engaging with uncertainty. But the fact that we're having this conversation at all, the fact that a single interstellar object can generate this much debate, speculation, and distrust, tells you something important. We're not ready. We're not ready for the discovery of extraterrestrial intelligence, not ready for the possibility that alien artifacts are already here, not ready to handle the social, political, and philosophical upheaval that would follow. And if 3I-ATLAS really is artificial, if the seeding is real, then ready or not, here it comes. Part 10. The Dark Forest Angle, Why a Seeder Ship Would Avoid Active Civilizations. There's a concept in speculative astrobiology called the dark forest hypothesis. It's borrowed from a science fiction novel, but the logic is chilling and, in some ways, compelling. The idea goes like this. The universe is a dark forest, and every civilization is a hunter moving quietly through the trees. You don't call out, you don't light fires, you don't reveal your position. Because if you do, if you make yourself known, you might attract something dangerous. Another hunter, older, stronger, more advanced, who sees you as a threat or a resource. So you stay silent, you stay hidden, and if you encounter evidence of another civilization, you don't approach. You either avoid them or eliminate them before they've become a problem. It's a pessimistic view of cosmic sociology, but it's not irrational. If resources are limited, if space is competitive, if civilizations are predatory, then silence is survival. And if the dark forest hypothesis is even partially true, it might explain why 3I-ATLAS avoids Earth. We're noisy, we're active, we broadcast radio signals, we light up cities, we change our atmosphere in ways that could be detected from light years away. We're visible. And from the perspective of a civilization following dark forest logic, that makes us dangerous. Not because we're powerful, but because we're unpredictable. We're a variable that can't be controlled. Now apply that to a seeding mission. If your goal is to introduce life or technology into a solar system, you want to do it quietly, without attracting attention, without triggering a response. You want your payloads to land in places where they won't be disturbed, where they can grow or replicate or spread without interference. Icy moons are perfect for this. They're remote, isolated, shielded by ice, and most importantly, they're not being actively monitored by an intelligent species. Earth, on the other hand, is crawling with humans. We have telescopes, satellites, probes, landers, rovers. We're nosy, we explore, we investigate. If something lands on Earth, or even near Earth, we're going to notice. We're going to study it. And if we detect alien biology or technology, we're going to respond, possibly in ways the seeders didn't anticipate. Maybe we'd quarantine it, destroy it, or try to reverse engineer it. Any of those outcomes disrupts the mission, so why take the risk? Why seed a planet that's already occupied by an intelligent, technologically capable species? Better to skip it. Better to focus on the quiet places, the places where your experiment can run undisturbed for millennia. Europa and Ganymede fit that description. They're hidden beneath kilometres of ice, protected from our prying eyes, stable over geological timescales. If you deploy payloads there, they stay hidden. They develop in silence, beneath the surface, where no telescope can see them, no probe can detect them, until they're so well established that discovery doesn't matter anymore. By the time humans drill through the ice, the seeding is complete. The oceans are full of alien life or alien machines, and there's nothing we can do about it. It's too late to stop, too late to contain, too late to prevent. We're just observers, documenting someone else's project. This strategy, seeding hidden environments rather than visible ones, is not just cautious, it's strategic. It minimizes detection risk, maximizes long-term success, and avoids conflict with existing intelligences. It's the dark forest logic applied to colonization. You don't confront, you don't announce, you infiltrate quietly, leaving no trace until it's too late for anyone to respond. And if humanity ever becomes a threat, if we develop the technology to reach those moons and interfere with the seeding, maybe the sentinels activate, maybe countermeasures are deployed, maybe the mission adapts. But until then, silence is maintained. The seeders remain invisible, and we remain ignorant. Now, the psychological implications of this are unsettling. If the dark forest hypothesis is correct, if civilizations are hiding from each other, avoiding contact, planting seeds in secret, then the universe is not a community. It's not a galactic federation where species cooperate and share knowledge. It's a battlefield, or at least a contested space, where everyone is paranoid, everyone is cautious, and trust is non-existent. In that universe, humanity's instinct to broadcast our presence, to send messages into space, to announce ourselves, is not brave. It's suicidal. We're lighting a fire in a dark forest and we have no idea what's watching. Some scientists and philosophers have argued for exactly this kind of caution. They've suggested that SETI, the search for extraterrestrial intelligence, should be passive, listening but not transmitting. That METI, messaging extraterrestrial intelligence, is reckless, potentially exposing us to dangers we can't anticipate. Those arguments are controversial, often dismissed as overly paranoid. But if 3I-ATLAS is a seeder ship, if it's avoiding Earth deliberately, then maybe the paranoia is justified. Maybe the universe really is a dark forest, and maybe we've been lucky so far, lucky that we're too young, too primitive, too insignificant to be worth targeting. But that luck won't last forever. As we expand into the solar system, as we send missions to Europa and Ganymede, as we drill into those ice shells and explore those hidden oceans, we're going to find things. Maybe we'll find native life, evolved independently. Maybe we'll find nothing, confirming the moons are sterile. Or maybe we'll find alien-seeded ecosystems, alien infrastructure, evidence that someone else got there first. And when we make that discovery, when we realise the outer solar system is already occupied, we'll have to decide, do we interfere? Do we try to stop it? Do we claim the moons as ours, even if they're already being used? Or do we back off, acknowledge that we're outmatched, and accept that the universe doesn't belong to us? That decision, if it ever comes, will be one of the most important in human history. It'll define our relationship with the cosmos, our understanding of our place in the galaxy, and it'll be shaped by fear, curiosity, and the realization that we're not alone, that we've never been alone, that the silence we've always heard from space isn't emptiness but strategy. Because maybe the reason we haven't detected alien civilizations isn't that they don't exist. Maybe it's that they're hiding, and maybe 3I-ATLAS, with its quiet trajectory, its precise targeting, its avoidance of Earth, is showing us how they hide. By staying out of sight, by working in the margins, by seeding worlds we're not watching. And if that's true, then the dark forest isn't just a hypothesis. It's the reality we're living in, and we're only just starting to see the trees. Part 11. Breaking Space. Research. Rogue plumes on icy moons. Is natural contamination already happening? Here's a twist that complicates everything. The icy moons might already be contaminating each other, naturally, without any help from interstellar seeders. Recent studies, some still in preprint, some published in specialized journals, suggest that moons like Enceladus and possibly Europa occasionally eject material from their subsurface oceans into space. Plumes of water vapor, ice crystals, organic molecules, all blasting upward through cracks in the ice propelled by internal pressure, tidal stress, or cryovolcanic activity. We've seen this directly on Enceladus, Saturn's tiny moon, where the Cassini spacecraft flew through plumes and sampled the material. The analysis revealed complex organic compounds, salts, and molecular hydrogen, all consistent with a warm, chemically active ocean beneath the ice. Enceladus is essentially venting its ocean into space, and that material doesn't just fall back. Some of it escapes, drifting through the Saturn system, coating nearby moons, even contributing to Saturn's E-ring, its natural panspermia, happening right now, without any alien intervention. And if it's happening at Enceladus, it could be happening at Europa, at Ganymede, anywhere with a subsurface ocean and enough internal activity to crack the ice. The question is, how much material gets spread, and where does it go? If plumes from Europa eject ocean material into space, some of that material will be captured by Jupiter's gravity, some will hit other moons, and some will drift into the wider solar system. Over millions of years, this could lead to cross-contamination, where organic molecules or even dormant microbes from one moon's ocean end up on another moon's surface, or buried in ice, or mixed into the regolith. Eventually, if conditions change, if ice melts or tectonic activity brings that material back into contact with liquid water, it could become active again. Life, or at least organic chemistry, could spread naturally between moons, creating a shared biosphere without any intentional seeding. This natural contamination process has profound implications for astrobiology. It means that if we find life on multiple moons in the same system, it might not represent independent origins. It might all trace back to a single origin, spread by plumes, meteorite impacts, or other natural mechanisms. That's still interesting, still valuable scientifically, but it's not evidence of multiple independent genesis. It's evidence of one genesis and subsequent dispersal. Now here's where it gets weird. What if 3I-ATLAS is exploiting this natural process? What if the seeding strategy isn't to deliver payloads directly to the ocean surface, but to deliver them into the plume zones, where natural ejection events will eventually carry the payloads into space and redistribute them across the moons. That would be elegant. You don't need precision landing, you don't need to drill through ice. You just need to place your payloads near a plume source, let natural activity do the work, and over time, your material gets spread across the system. Passive seeding, assisted by nature. It's cost-effective, low risk, and almost impossible to detect. The problem is that this makes contamination, natural or artificial, nearly impossible to distinguish. If we drill into Europa and find microbial life, how do we know if it evolved there, if it was spread from another moon via plumes, or if it was introduced by an alien seeder using plumes as a delivery mechanism? All three scenarios could produce similar results: life in the ocean, organic chemistry on the surface, biosignatures detectable by our instruments. Without a detailed genetic or biochemical analysis, without comparing the life we find to known terrestrial life and hypothetical alien life, we can't tell them apart. And even then, if the alien seeder used Earth-like biochemistry deliberately, if they designed their payloads to blend in, we might never know. This is the nightmare of ambiguous contamination. Every discovery becomes suspect, every result requires caveats, and the dream of finding unambiguous, native alien life slips further out of reach. So what do? One option is to accept the ambiguity, to recognise that the solar system is a dynamic, interconnected place where material moves between worlds, and that purity is an illusion. We explore, we document, we analyse, and we build models to explain what we find, knowing that our conclusions will always carry uncertainty. Another option is to focus on environments that are less likely to be contaminated, places where plume activity is minimal or absent, where natural cross-contamination is unlikely. Callisto, for example, is farther from Jupiter, less tidally heated, possibly more isolated. If we find life there, it's more likely to be native. Or maybe we focus on entirely different systems, exoplanets around other stars, where natural contamination from our solar system is impossible. But that's decades or centuries away. The reality is that contamination, whether natural, artificial, human-caused or alien-caused, is an unavoidable part of space exploration. The universe is messy. Material moves. Life, if it exists, probably spreads. And our job as explorers is to figure out the history, the origins, the pathways, even when the evidence is ambiguous. 3I-ATLAS, if it's a seeder, adds another layer to that complexity. It suggests that contamination isn't just a local phenomenon, limited to the solar system, but a galactic one. Material, life, technology, all spreading between stars carried by comets, probes, natural ejections, creating a web of connections that spans light years. In that universe, every world is potentially contaminated, every biosphere is potentially mixed, and the idea of finding truly native, isolated life becomes almost fantastical. Maybe that's the real revelation. Not that 3I-ATLAS is a seeder, but that seeding, spreading, cross-contamination is the natural state of the galaxy. And we're just waking up to that reality. The cosmos isn't a collection of isolated labs where life experiments run independently. It's a network, a garden where everything is connected, where seeds blow in the wind, where what grows in one place eventually spreads to another. And if that's true, then the question isn't whether Europa or Ganymede are contaminated. It's what kind of contamination, from where, and what it means for the future of those worlds, and for humanity's place in a universe far more entangled than we ever imagined. Part 12. New Physics and Stellar Dynamics. Are we overlooking migration corridors? Let's shift gears and talk about highways in space. Not literal roads, obviously, but pathways through the galaxy, routes that objects naturally follow, shaped by gravity, stellar motion, and the structure of the Milky Way itself. Theoretical astrophysics has long recognized that the galaxy isn't uniform. Mass is concentrated in spiral arms, in molecular clouds, in clusters of stars. And that mass distribution creates gravitational gradients, currents in the fabric of space-time that influence how objects move. Rogue planets, free-floating asteroids, interstellar comets, all of them drift through the galaxy following these currents, taking paths of least resistance. Some recent modelling work based on galactic dynamics and microlensing surveys that detect dark, non-emitting masses suggests that these paths might be more structured than we thought, that there might be corridors, relatively narrow lanes through the galaxy where interstellar objects naturally cluster, moving together, following similar trajectories. Think of them as cosmic trade routes, not built by anyone, but carved out by the geometry of the galaxy itself. If these corridors exist, they have profound implications for interstellar travel. Any civilization trying to send probes between stars would naturally exploit them. You don't fight against the current, you go with it. You launch your probe along a corridor, letting galactic motion carry it most of the way, using minimal energy for course corrections. It's efficient, predictable, and repeatable. And if multiple civilizations figure this out independently, if they all use the same corridors, then those corridors become busy, crowded with probes, artifacts, maybe even debris from ancient missions long forgotten. Now apply that to 3I-ATLAS. If its trajectory aligns with one of these corridors, if it's riding a galactic current toward the solar system, then its arrival isn't random. It's part of a larger flow, a migration pattern that might include dozens or hundreds of other objects, most of which we haven't detected yet because they're too faint, too small, or moving in ways that don't catch our attention. But they're out there, following the same route, arriving at similar intervals, targeting similar destinations. And if that's true, then 3I-ATLAS is just the first we've noticed, the tip of a much larger wave. This changes the stakes dramatically. Instead of a single, isolated cedar ship, we might be dealing with a fleet, a coordinated effort spanning centuries or millennia, using the corridor as a delivery mechanism. Each object in the fleet carries payloads, each one targets a different planet or moon, and together they seed the entire system, ensuring redundancy, maximizing success. Some payloads fail, some succeed, but over time the cumulative effect is undeniable. The system becomes colonized, not all at once but gradually, quietly, object by object, until the infrastructure is in place and the seeding is complete. That's a worst-case scenario for humanity, because it means we're not dealing with one event but with an ongoing process. Even if we intercept 3I-ATLAS, even if we prevent it from deploying payloads, more objects are coming. The corridor funnels them toward us, and we can't stop the flow without fundamentally altering the structure of the galaxy itself, which is obviously impossible. The evidence for corridors is still preliminary. Most of it comes from simulations, models that trace the motion of particles through the galaxy over millions of years, looking for patterns, clustering, preferred trajectories. Some observational data supports it. Certain regions of the sky seem to produce more interstellar visitors than others, suggesting that objects are entering the solar system from preferred directions. But the sample size is small. We've only detected 3 confirmed interstellar objects, and statistical patterns require far more data. Over the next decade, as new surveys come online, as telescopes like the Vera Rubin Observatory start scanning the sky every few nights, we'll detect more interstellar visitors. If those visitors cluster along specific trajectories, if they all seem to come from the same region of the galaxy, then the corridor hypothesis gains strength. And if they all show similar anomalies, similar compositions, similar targeting behavior, then the artificial probe hypothesis becomes harder to dismiss. Pattern recognition is powerful, but it's also dangerous. Humans are wired to see patterns even when none exist. We see faces in clouds, constellations in stars, meaning in randomness. So any clustering we detect in interstellar visitors has to be scrutinized carefully, tested against null hypotheses, checked for selection bias. Are we seeing a real pattern, or are we just noticing the objects that fit our expectations? That's a question that can only be answered with rigorous statistical analysis and more data. But if the pattern is real, if corridors exist and are being used, then the implications extend far beyond 3I-ATLAS. The galaxy might be crisscrossed with these routes, invisible highways connecting stars, facilitating the movement of objects, probes, maybe even information. Advanced civilizations might map them, use them routinely, building infrastructure along the corridors, placing relay stations, sentinel nodes, resource caches. The corridors become the backbone of a galactic transportation network, a framework that turns the Milky Way from a vast empty desert into a navigable space. And if humanity ever develops interstellar travel, we'll need to learn those routes, to understand the corridors, to navigate them safely. But we might not be alone on those highways. We might encounter traffic, artifacts left by others, contested zones where multiple civilizations have overlapping claims. The frontier becomes a negotiation, a balance of power, a game of cosmic diplomacy that we're not prepared for. That's decades or centuries in the future if it happens at all, but the seeds of that future might already be arriving. 3I-ATLAS might be part of the early stages, a probe testing the system, marking it, seeding it, preparing it for something larger. And the corridor it followed might be the route that future visitors use, again and again, until the solar system becomes a waypoint, a station along a route, rather than a destination. That's a humbling thought. We've always imagined ourselves as the centre of our own story, the explorers, the pioneers. But in a galaxy with corridors, with migration routes, with infrastructure, we're just another stop along the way, and the story is much bigger than us. Part 13, Astrobiology, Cryogenic Life, Ice Worlds and the Resurrection Hypothesis. Life is patient. That's one of the core lessons of astrobiology. On Earth, microorganisms have been found, in permafrost, frozen for tens of thousands of years, and when thawed, some of them wake up. They metabolize, they reproduce, they resume life as if no time had passed. Spores can remain dormant for centuries, waiting for the right conditions to germinate. Seeds buried in dry soil can sprout decades later when water returns. Life doesn't need to be constantly active to persist. It can wait. And if it can wait on Earth, under relatively mild conditions, imagine what it could do in the extreme cold of interstellar space, in the ice of a comet, in the frozen shell of a distant moon. This is the resurrection hypothesis, the idea that life or lifelike systems can remain dormant for extraordinarily long periods, eons even, and then reactivate when conditions change. It's not just speculation. Laboratory experiments have shown that organic molecules, complex ones like amino acids and nucleotides, can survive in cryogenic conditions, preserved in ice or solid carbon dioxide for extended periods without degrading. Some research suggests that under certain conditions, these molecules can even undergo chemical reactions when exposed to radiation or electrical fields, reorganizing, complexifying, potentially forming protobiological structures. It's early-stage chemistry, not fully alive, but not completely inert either. A kind of twilight zone between chemistry and biology where the line blurs. Now imagine a payload delivered by 3I-ATLAS, buried in the ice of Europa or Ganymede. It contains spores, dormant cells, or maybe something more exotic. Engineered molecular structures designed to self-assemble when exposed to liquid water and energy. For centuries or millennia, that payload sits frozen, inert, protected by the ice, shielded from radiation, waiting. Then, something changes. Tidal heating increases, cracking the ice, creating pockets of liquid water, or a human drill pierces the shell, releasing heat and mechanical disturbance into the environment. Or a natural plume event ejects material from deep in the ocean, carrying warmth and chemical energy upward. Any of those triggers could activate the payload. Ice melts, water flows, temperatures rise, and suddenly the dormant structures wake up. Spores germinate, cells divide, molecular machines begin their programmed tasks. The seeding enters its active phase, and what was sterile becomes alive, or at least occupied. This is the resurrection hypothesis applied to alien seeding. The payloads aren't meant to be active immediately. They're designed to wait, to survive the long journey and the long dormancy, and to activate only when conditions are optimal. That way, the seeders don't waste resources on environments that aren't ready. They plant seeds everywhere, and only the ones that land in favourable conditions ever sprout. It's a strategy of patience and redundancy, betting on time and probability rather than precision and control. For humanity, this creates a terrifying risk. If we send missions to Europa or Ganymede decades from now, if we drill into the ice and explore the subsurface oceans, we might be the trigger. We might be the ones who wake up something that's been dormant for centuries. And once it's awake, once it's active, we can't put it back to sleep. We can't uncontaminate the ocean. Whatever we've released, whatever we've activated, spreads, grows, and establishes itself. And we're responsible, even if we didn't know, even if the payload was planted long before humans ever existed. The ethical implications are staggering. Do we have the right to explore if exploration carries the risk of triggering someone else's project? Do we have an obligation to leave those worlds alone, untouched, pristine, even if they might not be pristine anymore? Or do we explore regardless, accepting the risks, trusting that the benefits of knowledge outweigh the dangers of interference? There's no consensus on these questions. Different scientists, different philosophers, different cultures would answer differently. But the questions need to be asked, and 3I-ATLAS, if it's a seeder, forces us to ask them. Because if the resurrection hypothesis is correct, if payloads are already waiting beneath the ice, then the clock is ticking. Every year we get closer to launching those missions. Every advance in our technology brings us closer to the moment when we drill through and encounter whatever is waiting. And when that moment comes, we need to be prepared, not just technically, but ethically, philosophically, psychologically. The flip side of the resurrection hypothesis is equally unsettling. What if the payloads don't need us to activate them? What if they're designed to wake up on their own, triggered by natural processes, environmental changes that happen over geological time? A slow warming of the moon's interior, a shift in tidal stress, a change in Jupiter's magnetic field, any of these could serve as a signal, a cue that it's time to activate. In that case, by the time we reach Europa or Ganymede, the seeding might already be underway. The oceans might already be filled with alien microbes, alien chemistry, alien ecosystems in their early stages of development. And we'd be arriving not as the first explorers, but as the first witnesses to someone else's terraforming project. That realization would be humbling and horrifying in equal measure. Humbling because it confirms we're not alone, that the universe is filled with life and intelligence. Horrifying because it means we have no say in what happens to those worlds, no control over their fate. They belong to whoever seeded them, and we're just visitors, interlopers, late arrivals to a process that started long before we even knew those moons existed. The resurrection hypothesis also raises the question of intent. Why design payloads that remain dormant for so long? Is it just a matter of efficiency, waiting for the right conditions? Or is there a strategic reason, a desire to avoid detection during the seeding phase, to remain hidden until the project is so far along that it can't be stopped? Both are plausible. Both suggest a level of planning and foresight that's deeply unsettling. Because if the seeders are thinking in terms of eons, if they're willing to wait millennia for their payloads to activate, then they're playing a game on a timescale we can barely comprehend. And we're just now realizing we're part of that game. Part 14. AI and Space. Could our own emerging tech mirror what an ancient civilization already does? In 2025 and 2026, artificial intelligence has made remarkable strides. Autonomous systems can now plan complex missions, optimize trajectories, analyze vast datasets, and even make decisions in real time without human input. Space agencies are already using AI for mission planning, satellite operations, and data analysis. It's not science fiction anymore, it's engineering. And as we look to the future, to missions that will explore the outer moons, land on asteroids, or even venture beyond the solar system, AI will be essential. We can't control spacecraft in real time across those distances. The light delay is too long. So we build systems that can think for themselves, adapt to changing conditions, and execute missions autonomously. It's the only way forward. But here's the unsettling part. If we can do this with a few decades of computer science and robotics, what could a civilization do with 1 million years of development? What could they build? The answer is almost unimaginable. They could create probes that are not just autonomous but intelligent, capable of learning, evolving, adapting to environments they've never encountered. Probes that can repair themselves, replicate using local materials, communicate across interstellar distances, and operate for eons without degradation. Von Neumann probes, named after the mathematician who theorized about self-replicating machines, are the logical endpoint of this technology. You send one probe, it arrives, it builds copies of itself, and those copies spread out, continuing the mission exponentially. One becomes many, many become millions, and eventually the entire galaxy is explored or colonized by descendants of that original probe. If 3I-ATLAS is artificial, if it's a product of such technology, then it's not just a comet. It's a machine, possibly intelligent, possibly self-aware, carrying out instructions programmed eons ago by a civilization that might not even exist anymore. It's a ghost ship, a relic of an ancient project still functioning, still executing its mission long after its creators have vanished or moved on. And if that's true, then the Jovian system is being seeded not by a living intelligence, but by an automated process, a machine following a program, indifferent to us, indifferent to the consequences, focused only on completing the task it was designed for. That's chilling because it means there's no one to negotiate with, no one to appeal to. You can't reason with a machine. You can't ask it to stop, to reconsider, to take our interest into account. It's just executing code, and unless you can hack that code or physically destroy the machine, it'll keep going until the mission is complete. Now, consider what humanity is building. We're developing AI-driven spacecraft, autonomous landers, systems that can navigate and explore without our guidance. We're not there yet, but we're moving in that direction. In a few decades, we might send our own probes to distant stars, equipped with AI that can make decisions, adapt, maybe even replicate if we figure out the engineering. And if we do that, if we send AI-driven seeders or explorers into the galaxy, we'll be doing exactly what 3I-ATLAS's creators might have done. We'll be adding to the network, contributing to the web of probes and artifacts that crisscross the Milky Way. We'll become gardeners ourselves, shaping distant worlds, planting seeds, building infrastructure, all through autonomous machines that carry our intentions but operate independently. The question is, will we be responsible gardeners? Will we consider the ethics, the consequences, the possibility that we're interfering with worlds that should be left alone? Or will we, like the hypothetical civilization behind 3I-ATLAS, prioritize expansion, colonization, and control, using technology to spread our influence as far and as fast as possible? There's no universal answer. Different human cultures, different political systems, different philosophies would approach this differently. But the fact that we're asking these questions now, before we've even left the solar system, suggests that we're aware of the stakes. We know that technology is powerful, that AI can amplify both our best and worst impulses, and that the decisions we make today will echo across centuries or millennia. If 3I-ATLAS is a mirror showing us what an ancient civilization did, then we need to look closely at that mirror and decide if we want to follow the same path. Do we want to be seeders, spreading life and technology across the galaxy? Or do we want to be explorers, observing, documenting, interfering as little as possible? Do we want to leave a legacy of gardens or a legacy of restraint? These are philosophical questions, but they're also practical ones, because the technology to become seeders is within our reach. Within a few generations, we could build the probes, launch the missions, and set in motion projects that outlast our civilization. And once those projects start, once the machines are out there, operating independently, we lose control. They become their own entities, autonomous agents pursuing goals we set but can't revoke. That's the lesson of 3I-ATLAS, if it's artificial. That technology, once unleashed, doesn't stop. It persists, adapts, and spreads, long after its creators are gone. And the universe fills up with machines, with artifacts, with projects half finished or completed eons ago, all layered on top of each other, creating a galaxy far more crowded and complex than we ever imagined. The gap between our technology and theirs, whoever they are, might not be as vast as we think. We're primitive, yes, but we're learning fast. AI is accelerating our capabilities, and within a century or two we might not be so far behind. We might even catch up, but by then the galaxy might already be full, already claimed, already seeded, and we'll be latecomers, trying to find our place in a universe that was mapped and managed long before we existed. That's a humbling realization, but it's also a motivating one. If we're going to compete, if we're going to have a say in the future of the galaxy, we need to move fast, think big, and be willing to take risks. And we need to watch 3I-ATLAS, study it, learn from it, because it might be showing us the future we're headed toward, whether we like it or not. Part 15. Cosmic Strategy. The Rise of Planetary Defense by Ignorance Doctrine. Let's talk about what happens next. Let's talk about policy, about how humanity should respond if 3I-ATLAS is indeed an alien seeder, or if the possibility is serious enough to warrant action. The traditional approach to planetary defense focuses on asteroids and comets that might collide with Earth. We track them, calculate their orbits, and if one poses a threat, we consider deflection missions, using kinetic impactors or gravity tractors to nudge the object off course. It's about physical protection, preventing impacts that could cause mass extinction. But what if the threat isn't physical? What if it's biological or technological? carried by an object that never comes close to Earth but targets the outer moons, traditional planetary defence doesn't cover that. There's no framework, no protocol, no international agreement on how to handle alien seeding or contamination scenarios, and that's a problem because 3I-ATLAS, if the hypothesis is correct, represents a new kind of threat, one that's subtle, long-term, and almost impossible to counter using conventional methods. So what do? One emerging idea, discussed quietly in some academic and policy circles, is what's being called planetary defence by ignorance. It's a controversial concept, almost paradoxical. The idea is that humanity's best defence against advanced extraterrestrial actors might not be strength or technology but invisibility. If we stay quiet, if we limit our broadcasts, if we avoid revealing too much about ourselves, our capabilities or our intentions, then we reduce the chances of being targeted or noticed. We become less interesting, less threatening, less worth the effort. Applied to 3I-ATLAS, this doctrine would suggest that we shouldn't interfere, shouldn't try to intercept or study. The object too closely shouldn't reveal that we've noticed anything unusual. If the seeders or their machines are monitoring us, if the sentinels are watching, then any aggressive action on our part, any attempt to disrupt the seeding, might trigger a response. Better to play dumb, to act like we're just a primitive species that doesn't understand what's happening, doesn't pose a threat. Let the seeding proceed, let the payloads deploy, and stay out of the way. Over time, maybe decades or centuries, we develop the technology and understanding to deal with the situation, but until then, we avoid provoking something we can't defeat. This is the logic of the dark forest applied to policy. It's cautious, pessimistic, and deeply cynical. It assumes that advanced civilizations are dangerous, that contact is risky, and that survival depends on staying hidden. Not everyone agrees with this approach. Critics argue that it's defeatist, that it cedes control to unknown actors, and that ignorance is never a defense. They argue we should be proactive, should study 3I-ATLAS intensively, should send missions to intercept it, or at least monitor its trajectory closely. If it's deploying payloads, we need to know. If it's seeding the moons, we need to document it, analyse it, and decide how to respond. That's the traditional scientific approach. Gather data, understand the phenomenon, then make informed decisions. But the tension between these two approaches, cautious invisibility versus active investigation, reflects a deeper uncertainty about how to engage with the cosmos. Are we explorers or prey? Are we participants or observers? Do we have agency, or are we just reacting to forces beyond our control? If planetary defence by ignorance becomes policy, if it's adopted formally or informally by space agencies and governments, it would reshape how we approach exploration. We'd be more cautious about broadcasting signals, more selective about what data we release publicly, more secretive about our capabilities. We'd avoid drawing attention, avoid revealing vulnerabilities, avoid doing anything that might be interpreted as hostile or competitive. And we'd monitor 3I-ATLAS and any future interstellar visitors from a distance, passively, without interfering. It's a fundamentally defensive posture, born from fear and uncertainty, and it might be the right approach, or it might be a tragic mistake, depending on what's really out there and what their intentions are. The problem with this doctrine is that it requires consensus, coordination across nations and agencies, and a willingness to suppress information that people might want or deserve to know. If 3I-ATLAS is artificial, if evidence emerges supporting that conclusion, can governments keep it quiet? Should they? The public has a right to know about existential threats, about discoveries that fundamentally alter our understanding of the universe. But releasing that information might cause panic, might trigger irrational responses, might undermine the careful strategy of invisibility. So there's tension between transparency and security, between democracy and survival. And there's no easy way to resolve it. Another aspect of this doctrine involves restraint in exploration. If the outer moons are being seeded, if alien projects are underway, maybe the best strategy is to avoid interfering until we understand the full scope. That means delaying missions to Europa and Ganymede, postponing the drills and landers, waiting until we have better technology, better understanding, better protection. It's frustrating for scientists who've spent careers planning those missions, who see the moons as the most promising targets for finding life. But if finding life means triggering alien payloads, if it means activating something we can't control, then maybe the delay is justified. Restraint isn't the same as surrender. It's strategic patience. It's recognizing that we're not ready, that the risks outweigh the benefits, and that sometimes the best move is to wait. But restraint also has costs. Every year we delay is a year we don't learn, a year our technology stagnates, a year someone else, some other civilization or machine, continues to shape the moons without our knowledge or consent. And if we wait too long, if we're too cautious, we might arrive at those worlds only to find they've already been completely transformed, that the opportunity to study pristine environments is gone forever. So there's no perfect choice. Every option carries risks and trade-offs. Act too aggressively, and you might provoke a response. Act too cautiously, and you might lose your chance. The planetary defense by ignorance doctrine is trying to navigate that space, trying to find a middle path that balances curiosity with caution, exploration with survival. Whether it succeeds depends on factors we don't control: the intentions of the seeders, the capabilities of their technology, the timescales they're operating on, and the degree to which they care about humanity at all. In the end, 3I-ATLAS, whether it's a comet or a seeder ship, has forced us to confront uncomfortable truths: that the universe might be more crowded than we thought, that humanity might not be the centre of anyone's attention, might not even be relevant to the cosmic projects unfolding around us. That exploration carries risks we're only beginning to understand, and that our survival, our success, our place in the galaxy might depend not on what we do but on what we choose not to do. That's a hard lesson. It goes against every instinct we have as a species, every drive to explore, to push boundaries, to reach out and touch the unknown. But maybe that's what growing up looks like, on a cosmic scale. Maybe maturity means recognizing when you're out of your depth, when the game is bigger than you, when silence is smarter than shouting. If 3I-ATLAS is a message, that might be the message. Not a greeting, not a threat, but a reminder. The universe is vast, ancient, and already occupied. And if we want to survive, if we want to have a future among the stars, we need to learn the rules, respect the boundaries, and accept that we're newcomers to a stage where others have been performing for eons. That's where we are now, watching 3I-ATLAS glide toward Jupiter, wondering what comes next, and realizing that the answer might already be written, in ice and silence, beneath the frozen oceans of worlds we've barely begun to understand.